Hello and welcome. Welcome to the last entry of the Composable chip, the creative coding epilogue. For those who don't know us, we are Nicole and Tasha, Android developers that met in droidcon New York this year. But I'll let Tasha introduce herself. Work. Ah, damn it. Probably going to need to do the secondary thing to post the first video.
Hey everyone, this is Tasha coming to you live from San Francisco.
Or not. It was working, then it didn't. What can we do? Okay, let's try again, shall we, folks? One more for Tasha. Work. Damn it, Tasha, come, don't be shy. And now it's not sounding, folks.
Hey everyone, this is Tasha coming to you live from San Francisco.
There it is. It worked. Something. We'll see how it goes. Anyway, don't worry. With that out of the way, what is this going to be about? We're going to be covering 4 main things. The first one is, of course, we're going to go over some basics of creative coding. Then, we're going to talk about how to do this creative coding in Compose. Afterwards, we're going to work on some basic toolset that we're going to be using in most of our examples. And lastly, and most importantly, we're talking about chip. Of course. Trippy one at that. So keep it with us. But without any loose time, let's start with some basics. And for that, let's answer our first question. What is actually creative coding? I mean, that's in the name of the talk, right? If you look for the definition online, you end up with something like this. Creative coding is a process where code is used to create something expressive rather than functional. Meaning that there's nothing going to be something super useful here for you. We're going to be doing fun stuff for the sake of it. So now that we know what we're going to be doing, how are we going to be doing that? There are different ways to do that, of course. This is expressive talk, so you can go wild and do whatever, but we're going to showcase a process that we like to follow. And the process consists of the next steps. First, you're going to draw something cool, something colorful. Then, you're going to morph it, meaning you're going to change some stuff. And lastly, of course, you're going to chip it. Fine. We can ignore the chip it part for now. That's optional, but highly recommended. But let's take a deeper look at the first 2 steps. And let's begin with drawing something cool. How do you draw something cool here? Well, no surprises here. First, you need to decide what you need to draw, or what you want to draw. It doesn't need to be something super incredible at the beginning. It can be something simple, like a boring square. Great. We're going for a great start. After you know what you want to draw, then you just need to draw it. Easy as that. But a small pro tip here, we highly recommend that instead of drawing one big blob of something, you use multiple points in there. Why we said that? Because you're going to have more points and more flexibility to play around with them. And instead of drawing a boring square like that, you can just, do something like a grid. Or, of course, a chip. Once you know what you want to draw, and you already know how you're going to be drawing it, the next step is to morph it. And in order to morph something, the first step is to decide what properties in there you're going to be changing. This can be something like color, it can be something like size, and once you decide which of these properties you're going to change, then you just need to change them smoothly over time, which coincidentally is the definition of morphing. For those that have been here for some time, this sentence right there may sound familiar. And that's because some people use this phrase exactly to define animations. So yeah, you got us. Our process, in summary, is to create an animation. But in this case, instead of layering everything of the work inside the animation framework, we're going to be drawing each of the frames ourselves. Don't worry, we're going to get to it. Don't be scared. So now that we know what we need to do and what we're going to be doing, how are we going to be doing this with Compose? So what do we need? Following our process, we only have 2 steps, right? we need to draw a bunch of points, and then we need to modify them. When we think of drawing, of course, the first thing you're going to think that we're going to use in the Android framework is canvas. But since we're going to be doing something interesting here, not only drawing squares and circles, we need to know a bit of maths. Don't worry, we'll be easy. Now, on the side of morphing things, of course, we're going to be using the animation framework in place, and again, some maths. So, answering our question of what do we need in order to do creative coding, we need canvas, we need animations, and we need maths. But let's take a deeper look, and let's just do a small overview of the specific things we're going to be using in each of these 3 topics, starting with canvas. As you all know, our canvas is used to draw things using coordinates. You can draw a lot of things here. You can draw squares, you can draw circles, you can draw chips, you can draw everything you want. But in this case, the most important part that we're going to use in canvas is this coordinate system and drawing circles. So, if there's anything we need to take from canvas, is to know how to draw a circle, which is as follows. You basically draw circle, you set a color, you set a radius, you pass a center in coordinates, x and y, and then you pass style. I hope this is not surprising to anybody. I hope everybody knows how to draw a circle. If not, there it is. Great. With canvas out of the way, let's jump into animations. What are we going to be using for animations? Of course, when one thinks of animations in Compose, the first thing that we think is in the animations APIs. Normally, these animations APIs are used to change things around, to change things slowly, to change colors, to change everything. Well, in this case, we're not going to be doing that. As I mentioned, we're going to be drawing each of the frames ourselves. So we're not going to be using most of the animation APIs. The only thing of what we're going to use from the animation framework is going to use it to track and handle our animation state. And how are we going to be doing that? Using the really aptly named animation state class. For those who don't know animation state, this is basically a class that contains all the information of the state of an animation. And once it is created, it can only be updated by animate2. Don't think too much about it. You can see a small example in here. Basically, you just create the thing and just change things and then just read things. That's everything this class is going to be, a container of our animation state. Nice. Now that we have the compose part over, what are we going to be using from maths? As we saw, maths are going to be used for drawing and for morphing. In the case of drawing, we're going to use them in order to plot points in our drawing, using coordinates, of course. And when we're talking about plotting points and using coordinates, of course, the thing you need to think on maths, if you remember your high school classes, is functions. We're going to be using functions to plot waves, to plot spirals, to plot things found in place. Now that we have things drawn using these functions, for morphing, we're going to use them to define changes over time. Now, again, if you recall your high school classes, most of the changes over time using these things also work with functions. So in summary, maths we're going to be used to use graph functions, plot them, and consume them. The functions that we're going to be using for drawing and morphing can look pretty similar, but they are not the same. The functions that we're going to be used for drawing, we're going to use functions of space, meaning that we're going to use them to find points in space and plot things. And the ones we're going to be using for morphing, we're going to be using functions of time, meaning that the time is going to be playing around with the values that we have in there, and things are going to change. Okay? Whew. Okay, that was a mouthful. But anyway, with all these basics in our belt, we should be ready to start with some basic toolsets. And for that, I'm going to give the word to Tasha, so let's see if this works. If not,
Thanks, Nicole. So in order to work with functions and time and have those change visual properties, I'm going to walk through a few ideas that we'll end up coming back to. So let's expand upon the extra steps of how we get these visual properties to change over time with functions. So we'd want to choose a function that would shape the kind of change that we're looking for, and then we'd want to know the output range of that function. Next, we'd want to know the range of values of the property that we're looking to change, and then finally map between those two ranges. This way, as the original function changes over time, we'd see a corresponding change in our desired visual properties. Let's take a look at some essential tools to do these range conversions. First up, we have lerp, and you might note this as linear interpolation. This one's good for mapping a value that falls between 0 and 1 to a value that falls between some custom range. And up next, we have norm, which is the inverse of lerp. And this is for normalizing the given value that falls between some random range and representing it as a value that falls between 0 and 1. So if we put the two together, we get the map function. This allows you to convert between two arbitrary ranges. You can imagine that this function can be pretty powerful because this means we can take any type of input, provided we know its range, and then represent it as any visual quality, such as a position or a size or even a color. So when incorporating time into the equation, using animation APIs to change every single property that we want can get quite tedious. Instead, we're going to take a look at the concept of a draw loop. A draw loop is the idea where you keep drawing frame after frame, and this is indeed how most screens and animations work. Small changes to what's drawn with every repetition will result in what we think of as an animation, such as in this pseudocode that represents a circle moving towards the right just because its x value is being incremented in a draw loop. We can get a quick draw loop using animation state and a loop in launched effect. And launched effect is essentially going to just launch a coroutine, and a while loop is going to continuously animate this animation state by some value that you can think of as the animation speed. These APIs allow us to customize the animation spec as well and to get much more control over how this animation state value changes over time. Now, if you wrap this around a canvas, we get a canvas that comes with a built-in draw loop. The onDraw parameter that we expose also includes the animating time value for use by the consumer. And we can also expose a parameter for the consumer to customize the speed of the animation. We're going to call this new animating canvas as a sketch for now, and the name is partly inspired by how project files are referred to in other creative coding frameworks like processing. Alright, so now that we've gone through some of those tools, I'm going to hand it back to Nicole so that she can get into how to draw some super trippy and funky sheep.
Great, it worked. I was not so sure. So thank you, Tasha. I hope you got all of that, especially the sketch part. But anyway, with all the theory under our belt now, you should be finally ready to the bulk of this talk, which is, of course, cheap. So, let's go and start with something simple, and let's draw a cheap spiral. Simple, right? Don't worry, we'll go step by step. And for that, let's go over our strategy again. As you may have remembered from the first section of this talk, the first step is to draw some points in place. In order to draw them, we're going to need to find a nice spiral function for that, right? Once we have this nice function, we're just going to draw it, and we have the spiral in place. After the spiral is in place, then we're just going to go crazy and start morphing things to see what things we can do that makes this spiral look a bit more interesting. And just doing that, you're already delving your feet into creative coding, folks. Congratulations. Anyway, let's go step by step. And first, let's talk about the function we're going to be using. This step normally involves a bit of researching, like you're just going to be fooling around into your nerdy math pages trying to find nice functions, but don't worry, I already did the net part for you. And I'm just going to tell you straight away that the function we're going to be using is the Archimedean spiral equation, which goes as follows. Don't be afraid, folks. It's just radius equals a constant times the angle. When you plot this equation right there, you obtain a spiral like the one that you can see on the left, right? Now, you may be wondering, hey, there's no x and y here. How are we going to be translating this thing to our canvas, right? Well, the reason there's no x and y here is because this equation is in polar coordinates. And before we can start plotting things in Canvas, we need to take a small detour and explain this a bit. So, The main difference between polar and Cartesian coordinates is that instead of using x and y to represent a point in our polar coordinates, which are the right ones, for the ones that we're wondering, use a radius and an angle to represent a point in the circular plot. Okay? Don't worry, we're not going to go further than this. The only thing you need to know is how to translate polar coordinates to Cartesian coordinates. And in order to do that, cosine and sine are again your friends. The only thing you need to do is do that. Radius times cosine or sine, the angle, and you obtain x and y. Great, not so hard, see? So once we already have our formula and our function to plot, the next step is, of course, to draw things. And in order to draw this cheap spiral, we're going to do as follows. We're going to go around a number of points. This is basically a number of points I want to plot in this spiral. And for each of those points, I'm going to be defining an angle. In this case, I just define a constant, and that's what I'm using. And then I'm just translating our previous Archimedean formula in there. Remember, radius equals constant times angle. Once we have a radius and an angle, we can easily translate those to Cartesian coordinates using the previous set formulas. And once we have x and y, you can plot a circle. Great. And just doing that, this is all the code you need to obtain a spiral. But there's something wrong here, right? This is supposed to be a cheap spiral, not a boring points one. So let's just fix that. So instead of calling our boring draw circle, we're going to call our friendly draw composable cheap function, which you can take a look in the code base, don't worry. As you can see, it receives the same parameters as the circle one. It receives a color, it receives a radius, and a center. So by all means, wherever you see a point, you can draw a chip. Great. So now that we have our spiral drawn, the next step is to morph it. So let's see what we can do in here. As I said in the beginning, this step is where the creativity comes in place. There's no set of instructions that you need to follow. This is where you go wild and just start, fooling around, changing things to see what happens. So, of course, I'm going to give you some tips. Some of the things that we like to change whenever we have plotted things or pulling graphs or pulling things is to spin things around. And in order to do that, the only thing you need to change is how we're obtaining this x and y. The only thing we need to do in this case is consider time for our angle. In this case, we're creating a new value called time-adjusted angle, and use that instead of the original angle to obtain x and y. Since we're not changing the original radius and angle, the form of the spiral is going to remain, but the things are going to shift a bit, and this is going to spin. If you want your spiral to spin faster, of course, you can just increase the values in there and play around. Now, great, this is looking better, but this is still a bit boring. Like, just using a plain color is not that great. So another tip for you is whenever you're working with angles and whenever you're working with polar coordinates, an easy win you can use is use hue. Why? Because hue also has a range of values from 0 to 360. So if you're using angles in place, you can just grab that angle, shove it into a color HDV formula, and obtain funny colors. Nice, this is looking better, but we can do something more. And another easy win for you is to just change the radius of each of the points. In this case, I'm just grabbing the big radius and just dividing it by 10. So the closer the chip is to the center, the smaller it's going to be, getting this nice infinity look. That wasn't so bad. We just changed it 3 things. And by changing 3 things, we pass from this boring blue spiral to a nice infinity colorful one. And this, folks, is creative coding. That's everything you need to do. So in case you were wondering, no, it's not hard. But that's it for this. Let's take a look at another example of spirals that you can do. In this case, you can also go wild in the draw step, and instead of just drawing and morphing things, you can also change formulas to change the way the spiral looks. And that's it. You can just grab the same code that we have, change the way you obtain radius and angle, and obtain completely different results. Great. So, having the spiral behind, let's take a look at another traditional example, which is using grids. So let's see if Tasha is not shy this time and wants to talk.
Thanks, Nicole. I'm sure that was pretty trippy. So while we have you hypnotized by the sheep spirals, let's start exploring how we can mess around with the sheep's fluff. So one of the ways of drawing the sheep's fluff is to use a grid of dots. And this allows you a few fun options because now you have control over moving the bulk of the sheep around. So we'll first take a look at how we can draw the sheep's fluff in the form of a grid, and then some ways of morphing it over time. Since a grid is two-dimensional, we can use 2 for loops to start laying it out. An easy way to get a uniform grid with equidistant points filling all available space is to first break apart the width and height of the available space into chunks or coordinates that fall between 0 and 1. This allows you to represent the grid as a set of points where each point has a value between 0 and 1. Then using our handy lerp function, we can represent them as actual XY offsets. So after drawing all those points and drawing a circle at every XY offset, we can get a grid that looks something like this. Well, that's great and all, but sheeps aren't squares. They're round and fluffy. So if we could just put the grid in a circle and make the grid as wide as the sheep's body, we'd be getting closer to our goal of representing the sheep's fluff as a grid. So here's math to the rescue again. Turns out there is a function that will tell us if a given point at an xy coordinate falls within a circle of a given radius and a center. And we can essentially use this formula while drawing our grid so that we only draw the points that fall within a particular circle that has a radius and a center. Here the radius would be the size of the sheep's body, and the center would be essentially the center of our canvas where our sheep is centered. Theoretically, if we did apply this function, we'd be able to cut out a circular grid from the square one. In code, we'd want to represent this function as returning a boolean. So it would return true if a given xy offset is truly within the circle and false otherwise. And we can plug that function straight into our grid drawing code and draw the bulk of our sheep using a circular grid. Now that we've made it this far, we can start morphing our grid. For each dot that we've drawn, we have control over its offset, its radius, and its color. So let's look at what kind of functions we can use to morph these properties. If you recall from earlier, our handy trig functions are periodic, and they have an output range of -1 to 1. We also know that if we plug in a value that tends towards 2 pi into these functions, we're going to get back a full cycle of output values. We can then use our map function from earlier to have these output values from trig functions influence the offset, radius, and color of our dots. So first, let's try an offset morph. 2 key things to note here. First, we plug in the UV values from earlier into our trig functions. Then we combine those with the time that we're getting from the sketch composable and 2 pi. Since u ranges from 0 to 1, we're just going to be taking fractions of 2 pi with this equation, essentially. So you can use either u or v here depending on the output that you're looking for. U will change things horizontally and v will change things vertically. Also note how we define the range conversion here. Note that the output of the sine function is going to be -1 to 1, so that's our from range, and our to range is going to be -15 to 15, and that's how much we're going to be influencing our x offset by. With this little shift in our x offset, we can then draw each dot on the grid, and we basically have an animated fluff. And you can tweak all the values that occur in this equation, including and especially a coefficient that you can attach to u. If you multiply u by any value, it's essentially going to increase the frequency of the sine wave with which these dots are moving. We can use the same pattern to influence the radius of our dots. Here we're going to use sine, but this time we're going to use the v coordinate so that we can see the changes take place vertically across the grid. The output range that we're going to define for our radius is going to be between 5 and 15 pixels. Now, as you can probably imagine, we can get really crazy with these trig functions. If we combine sine and cosine to change the radius, and change both x and y offsets together, we're going to start seeing these blobs of changes take place across the bulk of the fluff. Finally, let's take this all the way and add a little bit of color to the fluff. The HSV function, which stands for hue saturation value, allows you to represent the hue of your color between 0 and 360. Knowing that range, we can map the radius range of the dots to a desired hue range. And here we've left out the saturation and value parameters, but you can imagine getting pretty crazy with this stuff and mapping those to even other functions. So here we finally achieved a satisfying level of trippy sheep fluff. And now back to you, Nicole, to take us on a walkthrough of fluffy pads.
Great. Thank you, Tasha.
Thanks, Nicole. I'm sure that was pretty trippy.
What is this? This is not the wand. What's going on? 1 second, folks. Technical difficulties as usual. Tasha likes to talk a lot. Great. As I was saying, thank you, Tasha. And now for the last example, we're going to be talking about fluff pads. So far, we already saw grids, we already how to plot different functions in place, and how to morph different values of it. But of course, chips are dynamic, so you can change them even a bit more. And in this case, we're going to be using pads for that. But I'm getting ahead of myself. Let's go over the strategy. So the strategy, following the previous steps as we have been discussing, first is to draw things. And in this case, we're going to be drawing the fluff using a pad. The strategy in specific is we're going to be going around the circle, because chips are circular in our case, and for each of the angles we stop with, we're going to be changing the radius. Again, another function for radius. Once we have that, we're just going to morph them over time, and that's how we're going to obtain this trippy-looking fluff in there. As you can see, for each point, the radius is oscillating between a minimum radius and a maximum radius over time. But let's jump into code. How are we going to be drawing this? We're going to be drawing it as follows. Of course, we begin creating a pad, and then we're going to going around the circle. We're working on radians, so of course it's to pi. For each of the angles in which we stop off, we're going to have a function for our radius. In this case, we're just going to grab a random value between minimum radius and maximum radius. Once we have that, we just create a point, again, transforming our polar coordinates to Cartesian. And once we have this point, we just add it in our pad. Once the pad is done, meaning that we went through the whole circle, the only missing step is to draw it. And just running this code, we obtain this fluffy chip. Great. As you can see, we're doing exactly what we said. We have different points in place, and for each of the points that are going in there, we're putting a value of the radius between minimum and maximum. Nice. Now that we have our spiky fluff drawn, let's start morphing it. As you saw, we're using a random value all the time for radius, so in this case, the only thing we need to do is grab our previous code inside a sketch. Sketch is already going to be forcing a redrawal over time, so let's see how this looks, shall we? Nice. It doesn't look so fluffy. What is going in here? As we mentioned, our radius is grabbing a random value. So there's no connection between the values that they can have. So that's why you see all this jumping around, minimum, maximum, having spikes around. So the question is, can we improve this spiky sheep? And the answer is yes, of course. And for that, we're going to use noise. Or more specifically, noise functions. So, what are noise functions? In summary, noise functions are algorithms that produce coherent randomness. This means that we're going to obtain a smoother value of random. This is because each of the values in this algorithm are related to the previous and next values. That's why when you go random, there's no relation between them, so the value can jump to minimum and maximum without any reason. But with noise, you get this wavy pattern because the next value is related to the previous one. Great, but how are we going to be obtaining those noise functions? We haven't talked about them before. Don't worry, we're not going to build them from scratch. That's crazy. There's already a library available for us, which is what we're going to use. and that is the Kotlin Graphics GLM. This is based on the OpenGLM mathematics library already in place, and it has a lot of really handy functions for graphics, and specifically noise. The only thing we need to do is add it to our projects, and voila, we have the functions. Nice. But what noise functions are in this library? What are we going to be using? In summary, there are two types of noise that we're going to be working with, and that is Perlin and Simplex. Both of them were created by Ken Perlin, and you can see a slight difference between them and the image on the left. All these functions have an output of values between -1 and +1, and they have as inputs a lot of vectors of 2, 3, and 4 dimensions that basically represent this noise in different dimensions, being 2D, 3D, 4D. But I'm going to stop here because I can go wild and can talk about noise the whole presentation, and that's not the point. So if you're interested more about noise functions, I highly invite you to watch this video, or list of videos, What is Perlin Noise by the Coding Train. Highly recommended. Great. Now that we know that we have noise functions in our grasp, how are we going to be improving our fluff pad? Well, let's go back to the drawing table and let's grab our code again. No surprises, the only part we need to change in order to get a fluffier fluff is the radius. Instead of using this randoming there, we're going to be using our GLM noise values. In this case, since I'm only interested in a circle, I'm going to use in Perlin on a 2-dimension. And once we have this noise, the only step missing is map this noise, remember, values from -1 to 1, to our radius. Great. And once we do this, the only thing that jumps into the face is this vector 2 with these x offsets and y offsets that we also haven't touched, right? Just to keep it short, these x and y offsets are calculated as follow, and this basically represent x and y coordinates in our 2D Perlin noise graph to obtain values in there. Again, I'm not going to go deeper than this. Just believe me that this is going to give you values that are cyclical. And again, if you're interested in learning more about noise, watch those videos. Nice. So going back, once we change this, create our noise, map this noise for radius, we obtain a fluffy chip. As you can see, there's no spikes in there again anymore. We now have a smoother fluff in place. Nice. So now that we have the drawing, how are we going to be morphing this thing? We need to morph it through time, right? So we're going to cheat a bit, and instead of going crazy and creating new things, I'm just going to change this vector right there from a 2-dimensional vector to a 3-dimensional vector and pass time. So yeah, I don't need to do anything else. Just doing that, you already obtain a really nice morphing fluffier chip. Nice. And of course, you don't need to stop there. You can grab and go wild, change values, change the noise that you use, or just go random. It doesn't matter. Whatever makes your heart happy. So just go around. I highly recommend you get the GLM library and start experimenting with noise and what things you can do with it. Great. But this is all you need. Noise and everything. So let's go to a small, little extra topic that we were not going to cover, but let's see how it goes. Shaders.
No creative coding talk would be complete without even the slightest mention of shaders. Since Android 13 has been making its rounds, we're going to dip into shaders just a little bit and take a quick look at how to use them with the help of our trusty sheep, of course. So what exactly are shaders? They're essentially just programs that determine a given pixel's position and color. They run per pixel on the screen in parallel, and probably the most important thing to note is that shaders only have information about the current pixel's position.
Yeah, I think we're going to need to do the video swap.
So in programming shaders, you have no access to information about neighboring pixels. This is one of the reasons...
Yeah. Sorry, folks. Tasha is shy sometimes, so maybe we can change the
video. That shaders can be so tricky to reason about, and why they have a reputation for being so hard to work with. Shaders are usually written in the OpenGL shader. No creative coding talk would be complete without even the slightest mention of shaders. Since Android 13 has been making its rounds, we're going to dip into shaders just a little bit and take a quick look at how to use them with the help of our trusty sheep, of course. So what exactly are shaders? They're essentially just programs that determine a given pixel's position and color. They run per pixel on the screen in parallel, and probably the most important thing to note is that shaders only have information about the current pixel's position. So in programming shaders, you have no access to information about neighboring pixels. This is one of the reasons that shaders can be so tricky to reason about and why they have a reputation for being so hard to work with. Shaders are usually written in the OpenGL shading language, which is a very C-like language, also known as GLSL. But today we're going to look at how we'd write them for use on Android. With Android 13, you can use custom programmable shaders, which means you can use any arbitrary shader as a brush when drawing. You just have to pass the shader code as a raw string into the runtime shader constructor and use the resulting runtime shader object to create a brush. Here the shaders will be written in AGSL, aka Android Graphics Shading Language. AGSL is kind of similar to GLSL, with which most shaders are written, so most of the time you can get by with tweaking GLSL to convert it to AGSL syntax. Gradient shaders are probably the simplest shaders to play around with. Here we're just using a simple one from ShaderToy, and it's been converted from GLSL to match AGSL syntax. ShaderToy and shaders.scale.org are places where you can discover and even edit shaders directly on the web. The latter is more useful for those of us on Android since you can directly edit AGSL. You create the runtime shader by passing the raw shader code into its constructor. Then you can create a shader brush with a resulting runtime shader. We can also leverage the time parameter in our sketch composable to cause the shader to animate, as we'll see in a bit. Shader brushes are pretty much just like any other brush. You can use them when drawing anything. So let's see how to paint our sheep with a shader brush and have it animate. Starting with our sketch composable that gives us an animating time value, we'll need to set up a few properties on our shader for it to render and animate. The shader will expect a few things to be set from the outside world. One of the most important things is that of the viewport resolution, or the eye resolution property, as the shader calls it. Since we're in the context of a drawscope body, the dimensions of our sheep are readily available, so we can set the eye resolution property on the shader using the width and height properties of the drawscope. Next, we'll want to pass the animating time value into the shader as well via the eye time property. And now finally, we're ready to use the shader as a regular brush. There's a little helper function that we created that draws the sheep, and we can pass it any brush we'd like. So instead of painting the fluff with a solid color or even a grid, we're just going to use the shader brush to render the animated gradient over all the fluff. There's a whole universe to explore with shaders, so if you find this stuff interesting, definitely check out the bookofshaders.com to learn more about them. And now, back to you, Nicole, to wrap this up.
Yes! Great! Thank you, Tasha, for that. Now, chipping up all of this. As we saw, we had a lot of examples on how you can start with this creative coding stuff. And there was no meaning behind it. It was just for the fun of it. So chipping up, this is our creative coding process that we highly encourage you to start with before you start experimenting around. The first step is to draw a bunch of points using functions. The next step is just to go wild and start morphing them. That's it. But remember, folks, the most important part of all of this is just to have some fun. And that's it, folks. Thank you. If you want to learn more, sorry. If you want to learn more, we highly recommend that you play with the repos, take a look at the coding trained and also the creative coding pages in place. If you want to take a look at the crazy maths and formulas that we added, this is the reference of our images, if you want to take a look in there. And lastly, we're going to be creating a Twitch stream where we're going to be hunting some spaceships and more. So, if you're interested in this crazy stuff and just want to see us fooling around, please stay tuned on Twitter. Thank you.